Hey guys, what's up? Today we're going to look at some heating curves. So essentially what these are looking at is they're looking at a single substance and taking it from a certain temperature to another temperature based on adding energy or taking energy away. So these are important because we can really see differences in terms of different materials. So different materials will have different heating curves, including different boiling point and melting points. They'll also have different heats of vaporization or fusion or whatever processes you're going under. So these are often used in conjunction with phase diagrams, which we'll talk about at a later date. And also they can be used just to compare different materials in different ways. So through our lab, through other interpretations of different information we get from this, like we can use the Clapeyron equation like we did in the laboratory to investigate other sort of processes between these materials. So hopefully you guys get a bunch of information out of this. I'm gonna just do a problem and kind of explain a little bit beforehand. Hopefully you guys like this. Let me know what you like, what you don't like, and any questions you guys have, be sure and send them to me or let me know. Thanks guys, enjoy. See you. Alright, hey guys, welcome back. So we're going to look at this phase change problem that I've kind of already set up here for you. In class you guys went over another type of phase change problem. It's similar but not quite the same, and I just wanted to go through one so that you guys could easily get another example of someone teaching it and maybe being able to understand it better. I suggest you try this problem before I go over it, just in case, just so you get a little practice. And of course go through the ones in your book. But let's start here. So compound xylene, essentially, we have 20 grams of this compound at about 15 degrees C, and we're able to add 10,500 calories to it. What we want to figure out is what temperature will it end up being. So I've already looked up a bunch of the information, including the melting point, boiling point, the heat of fusion, the heat of vaporization, and the specific heats for each of the phases that xylene can be in. So looking at this, we have to think what will happen to our material. So if we're going to do a phase diagram here, phase change, here we go. So looking at this, we always have temperature over here, and we're going to have heat added as our x-axis. So essentially what we're doing is we're starting with some material, and I'll change the color. Let's go with this color. So we have some material at 15 degrees C. Alright, so for our first amount of heating, until we get up to 25 degrees C, we're just causing the temperature of that solid to rise. So we heat it up some until we're at 25. Once we're there, we've hit the melting point of xylene. So what's going to happen is we're going to actually initiate a phase change from solid into a liquid material. So when we do that phase change, the important thing to keep in mind is that temperature won't change. So essentially what happens is all of that solid has to melt before it can increase in temperature again. This is just something we've observed, and actually something you can observe yourself. If you take a thermometer and put it in like a glass of ice or something like that, and you start to heat it up, you should, as long as you're stirring properly, see the temperature not drop until all of the ice has gone. This is just something that we've observed a long time, and it's actually pretty cool because you can do it yourself. So we've started as a solid here, and in this next step we've gone from a solid to a liquid, and otherwise we've melted. So we've melted here, right? So I'm showing phase changes as red, just to keep it different. So once we've melted, we've become a liquid, right guys? So you guys know that. So now we're a liquid at 25 degrees C, and it looks like we can heat up to 80 before any other phase changes occur. So we're going to start heating up until we get to 80 degrees C. So now we're at 80. At this point, we're going to go from a liquid into a gas phase, and again we have to remember we don't change temperature. So you can see that first off, one thing to keep in mind is it should take a lot more energy to vaporize something than it does to melt it. So usually if you're drawing these things to kind of keep track of what's going on, the vaporization step will have more heat in it than a melting step. Vaporization. It's hard to write on this thing. There we go. Good enough. So once we vaporize this material, we're now in a gaseous state, right? So now that we're in a gas, we're going to have some energy left over, we assume. And so what we can do is we keep heating this material up to some temperature. We're not 100% sure where we go because we're given a calorie unit, not an end temperature, so we have to figure that out. Alright guys, so looking at what we've done so far, let's figure out a way to mathematically solve this problem. So if we think about it, if we start all the way down here at 15 degrees C, we first heat up our solid, then melt it, then heat up our liquid, then vaporize it, then heat up our gas. And so the amount, since this is graphed as temperature versus energy, we can actually say that all the energy it took to get to this last temperature, we don't know what it is yet, but all the energy it took will be equal to 10,500 calories, right? Because that's how much we put in. So what we can do is say that 10,500 is going to be equal to the energy that we added in to heat up the solid, plus the energy that it took to melt the material, plus, let me move this over really quick, there, that's better, plus the energy that we added in when it was a liquid to heat up the liquid, plus the energy that it took to vaporize the liquid and turn it into a gas, and then finally plus the energy that we added in when it was a gas to heat up the gas. So we know that the total energy, 10,500 calories, has to be equal to these processes. So if we know that, we can actually go through these and start to plug in information we know and eventually solve for unknowns. So let's think about what we have here. So 10,000, so let's just look at each individual piece. So if we think about E, the energy that was added to the solid to heat it up, well, we know we have the specific heat, so if we look at that, 0.25 calories per gram C, well, we need an energy unit out. So if we want to look at just energy, we'll need to get rid of grams and degrees. Well, we know we have 20.0 grams, and we also know that when we were a solid, we went from 15 to 25 degrees, so the difference would be 25 minus 15 C. So doing this, we'll end up with, we'll get the energy out for E sub S. So if we do that again for E sub L, we have a different specific heat now of 0.30 calories per gram C. We still have the 20.0 grams, but now our delta C is going to be a little different. When we were liquid, we went from 25 to 80 degrees C. So our difference would be 80 minus 25. So hopefully you guys are following along. Lastly, let's figure out the amount of energy that we would have had as a gas. So if we do E sub G, that's going to be equal to our specific heat of a gas, which is 0.20 calories per gram C. We still have 20.0 grams, so we're good there. And then lastly, we started at 80 and we went to, well, we don't know. That's what we're trying to find out. So since we're trying to find out the temperature, we know that it's going to be X minus 80 C. Oopsie. So essentially, this is our unknown here. So I'm going to label it some crazy green color. That's hard to see. I'm going to label it some crazy, this color, brownish color. So we're looking for that X. That's what we're trying to find out, the final temperature that the gas ended up as. So along with this, we need to figure out what was the energy we put in to melt our system and vaporize our system. So let's go ahead and look at those individually now. Let's first do the melting process. So in order to melt our material at 25 degrees C, we essentially put enough energy in for each gram to break the bonds enough to where they were no longer in a structured lattice, but instead in a liquid form. So to do that, we use the delta HF. So that's 120 calories per gram. So it took 120 calories per gram of our material to break it apart into liquids. So we need to, in order to get to just an energy unit, we have to multiply by our mass. So you can see here that if we multiply by our mass, we'll end up with just an energy unit. Lastly, real quick, let's go ahead and do the E of vaporization. I'm going to extend that. And so this again is going to be the enthalpy of vaporization. So here we have delta HV is going to be equal to 360 calories per gram. So 360 calories per gram. We're going to have to get it into just energy units. And so if we just do that, we'll end up with our answers. So we have all these materials here, and we have one variable x. So if we plug all this math in essentially into this equation, we should be able to solve for x. I'll be right back when I've got all those numbers for you guys. Be right back. Alright guys, welcome back. So I've done some of the math here, and so you can see that essentially in order to heat up our solid, it took 50 calories of energy. To heat up our liquid, it took 330 calories of energy. To melt our solid, it took 2,400 calories of energy. And to vaporize our liquid, it took 7,200 calories of energy. So I've taken these values here and I've plugged them into our equation here. So you can see that our total is equal to these values, which is just from this math up here, plus our E of the gas, our energy that was in the gas, but I didn't calculate it out since we have an unknown. So the first thing I'm going to do is just get everything over here. I'm going to try and just simplify the equation and solve for x. So essentially what I'm going to do, to both sides I'm going to subtract 50, I'm going to subtract 2400, I'm going to subtract 330, and I'm going to subtract 7200. So doing that, I end up getting 520 calories is going to be equal to what I have left, which is just the information about the gas material. Oops. 0 grams times x minus 80 C. So we end up with this value here. So all we have to do this is just take the whole thing, and I'll go ahead and write because it's hard to do otherwise. I'm going to head and divide by, so I'm going to divide all of this material by 0.20 and 20.0 in order to get rid of these values over here. So then if I do that, we're going to end up with 130 C is going to be equal to x minus 80 C. So then finally the last step is just going to be adding 80 to both sides, and so x is going to equal, in this case, 210 degrees C. And that's your answer. That's the final temperature. So we know that this essentially gets all the way up to 210 degrees Celsius. So that's a big problem, a big problem here. Like, there's a lot of steps, and so what I really want you guys to take home is realize that no matter what you're looking at here, if you're looking at these phase changes, the summarization of each of the steps is going to equal the total. So whether you don't know the total or you don't know a piece of one of the steps, you can always find it as long as there's only one missing piece. And that's really what I wanted to emphasize here. Just make sure you can look at these and kind of figure them out. Sometimes they're a little more difficult, but I think you guys can do them as long as you follow these basic steps. Alright, so that's it for today. I'll see you guys in a second.